Hey everyone, welcome to the live class. We'll wait one more minute and then I'll start. You guys can hear my voice and see the board, right? Good. So, uh, let's wait one more minute. Okay, so in the last few classes, I did composition of matter, atomic structure, and in this class, I'll do chapter number 3, which is the periodic table of elements. Remember, this is the IMAT chemistry syllabus, right? From the IMAT syllabus of 2022. The 2023 syllabus is not out yet, so we are following the old syllabus. So in this video class, I'll do chapter number 3, which is about the trends and the different types of trends that happen in groups and elements. So basically, trends in the periodic table. Now, remember, in the exam, you won't get the periodic table. So in the last class, I tried the sample question again when I asked, give me a different answer. Uh, it's about biology, right? Send me that question in the Discord. Whatever you have any questions, send me on Discord. I'll answer it there. But right now, let's not waste our time. Okay, so this is the periodic table, right? You don't have to memorize anything because if there is a question related to the periodic table, they'll give you the elements which is related to the question. But what you need to know is groups and periods. So what is a group? A group is when you go down or up. So this right here, right? This is a group. This is a group. And a period is when you go from left to right or right to left, right? So this entire thing is one period. So this entire thing, helium and hydrogen are considered period. So this is period number 1, this is period 2, this is period 3. And groups, this is group number 1, this is group 2, this is group 3, group 4, 5, and so on. Now, in for the exam, right? Let's start with the atomic radius first, because if you get this concept, then everything from here on will get very easy. So don't mind my writing, but what is periodic trends? The atomic radius will decrease from left to right. So across a period, right? Across a period, left or right, the atomic radius would decrease. Why is this? And what is atomic radius? Atomic radius is, let's say uh, this is the nucleus, and then this is the atomic radius where the electrons are on the radius. So this is one atomic radius, this is the second, and down across a group, across a period, the atomic radius would decrease because the charge on an element increases. What do I mean by charge? Charge, simply said, is the proton number of that element. So you can see that across a period, right, the proton number is increasing. So it's 19 here and it's 36 here. So across a period, the charge is increasing. This is one of the reasons that the atomic radius decreases. So the first is that the charge or the positive charge decreases, increases across a period. The second thing, the second reason that uh, the atomic radius decreases is because of something called the shielding effect. So because of the shielding effect, the atomic radius would decrease across a period. Across a period, left to right. What is shielding effect? Shielding effect, right, is when two electrons will repel each other. So uh, in this in this what do we call this? Orbit, right, there is one electron, and let's say in this orbit, orbit number 1, there is one electron. Now these two electrons will repel each other, so the atomic radius would decrease. But wait, shielding effect in across a period, right? Shielding effect across a period will remain constant. Why is that? Shielding effect remains constant. Why is that? Because across a period, right, you can see that the change in the number of electrons, right? So there is 19 electrons for potassium, but calcium, going from potassium to calcium, you'll only gain one electron. So will the group increase in the number of shells? No, because let's say this is potassium. Let's say this is the outermost shell of potassium. It has 19 electrons, and for uh, calcium, right, it gains one electron. So the shell would not increase simply because you can gain one electron in this shell right here. So the shell number won't increase, so there won't be any other shell. So the shielding effect would not be that strong because there is no shell that is increasing. The electron, which is only gained by one electron, can come in the same shell as the previous element's electron. So the electron would not increase in the shell. It would remain in the same shell. So the shell number doesn't increase, therefore shielding effect remains constant. These are two main reasons that the atomic radius decreases across a period. Number one, the charge of an element increases. Number two, the shielding effect will remain constant. Because of this, atomic radius decreases across a period. Now, what happens down the group? What happens when I go down anywhere in the group, meaning boron to gallium or nitrogen to bismuth? What happens here? So the atomic radius increases down the group. The atomic radius increases down the group. Why is this? Because number one, you can see that the biggest reason for this increase is shielding effect. So this was across a period, right? Now comes down the group. So down the group, the atomic radius would increase because of shielding effect. This is the biggest reason why the atomic radius increases down the group. So what it simply means is that you can see that uh, this the first element in the group has 9 electrons, but when I go to the last group, right, it has 85 electrons. That is a huge number. So when I draw, let's say I draw, this is for boron. Let's say this is boron is where is boron? Boron has 5 electrons and helium has 81 electrons. So this is let's say this is the outermost shell. And for helium, right, helium, the number of shells would be huge. So the number of shells would be very big because the electron number is increasing by a big margin. Down the group, the electron number increases by a huge margin. So the shielding effect would be much, much greater because since there is more shells, more electrons will repel each other, more electrons repel each other, right? So the electron shells move further away from each other because look, this electron will repel this electron. So when that happens, they repel each other. So this electron shell would move further away. Similarly, these two shells would move further away because these two electrons are repelling each other, right? So down the group, the atomic radius increases because of shielding effect. Now, you guys might be thinking that the charge is also increasing, right? The charge is also increasing by a huge margin. You can see that there is 9 protons in fluorine, but there is 85 protons in astatine. And this is also a valid point, but remember that positive charge is not having that much effect compared to the shielding effect. So the shielding effect outweighs the positive charge effect. So that was atomic radius. atomic radius decreases across a period. So going left or right, going from decreases from left to right. So when you go from here to, let's say, here, the atomic radius decreases. But if you go down the group, the atomic radius would increase. That was atomic radius. Now, I'll talk about ionization energy. So we're done with atomic radius. Now let's get to ionization potential and electron affinity. Ionization potential is another name for ionization energy. Now, where is ionization energy? Uh, so so what is ionization energy? Ionization energy is the energy required to remove an electron from an atom or an element, right? Let me find electron ionization energy. Okay, so down the group, right? When you go down the group, ionization energy would increase. Ionization energy, sorry, decreases. So going down the group, ionization energy decreases. Why is that? Because I told you earlier, atomic radius going down the group increases. So let me explain you in a different way. So let's say this is down the group, right? So these are some elements. And when you go down the group, the ionization energy decreases. Why is that? Because the number of electrons or the atomic radius increases down the group. So this is the positive charge, and this is the protons in the nucleus, and these are the electrons. So these are electrons. So when the atomic radius gets bigger, the attraction between the protons and electrons would decrease. So attraction decreases, therefore ionization energy would decrease down the group, because now you need less energy to remove an electron. Ionization energy is the energy required to remove an electron from an atom, and when the atomic radius gets bigger, the electrons and protons have less attraction between them. So you can easily remove this electron because the proton is not attracting this electron very much. So ionization energy decreases across a period, but across a group, sorry, down the group, ionization energy would decrease. But what about across a period? Let's say you move left to right across a period. By period, I mean going like this. What would happen across a period? I told you earlier, the atomic radius, decreases. The atomic radius across a period decreases, right? So this atomic radius decreases. The atomic radius would get smaller because of shielding effect, and the proton and the electron will have greater attraction. And because of this greater attraction, you would need more energy to remove an electron. So ionization energy across a period would increase. Ionization energy increases across a period, but decreases down the group. All right. So this is the same case for electron affinity. What is electron affinity? Electron affinity is the energy released when you remove an electron. So energy released when you remove an electron. And this is the same concept with ionization energy and electron affinity. So ionization energy and electron affinity both decreases down the group, but increases across a period. So now we are done with ionization energy, electron affinity. And in a summary, right, you can basically learn this concept that ionization energy across a period would increase. It would increase. Across a period, electron affinity also increases, but the atomic radius across a period, right, would decrease. So atomic radius decreases across a period. And down the group, atomic radius would increase. So going down the group, atomic radius increases. Because of this, the electron affinity and ionization energy going down the group would decrease. Or vice versa, when you go up, the ionization energy and electron affinity increases, right? And this I'll explain later. So now that we're done with periodic trends, I'm moving on to the different types of groups and uh, the the different types of groups in a periodic table. So let me just erase all of this, right? Or you know what? Let me copy this and paste it somewhere else. So yeah, here. Now, so these were groups, right? When you go down, it's called a group. When you go across, it's called a period, right? Now, the IMAT expects you to know the different types of groups in the periodic table. So these right here, right? This group right here is called the halogens. This group right here, fluorine, chlorine, bromine, iodine, is called the halogens. And the last group, which is known as group 0, is called the noble gases. So this right here is called the noble gases. And I'll explain all the trends later on. For now, just learn the names, right? This group is group 1, and similarly, this is group 2, right? And both of these groups are called the alkyl alkali metals. Why is that? Again, I'll explain this. For now, just know group 1 and group 2 are called the alkali metals. And this group right here are called the transition elements, right? Group 1 alkali metals and second one is alkali metal. Yes, group 1 is alkali metals, second one also are alkali metals. So let's go to group 1 first. Group 1 metals are known as they are not, uh, wait, I'll get to that part, but let's study group 1 first. Group 1 metals are known as the alkali metals because they form alkali solutions when they react with water. And group 1 metals are lithium, sodium, potassium, rubidium, cesium, and francium. So group 1, lithium, and all of these are group 1 elements, and they are called the alkali metals. And the alkali metals share similar characteristic chemical properties because they each have one electron in their outermost shell. So the outermost shell electrons are called the valence electrons, right? And they all share the same electron in the outermost shell. And some properties of alkali metals are they are soft metals, which can be easily cut with a knife. They have low densities and low melting points, and they are very reactive. They only need to lose one electron to become stable. So alkali metals are soft, and the first three alkali metals are less dense than water. So lithium, sodium, potassium have less density compared to water. And they all have low melting points, which decreases as you move down the group due to the decreasing attractive forces between outer electron and positive ion. So this is related to the atomic radius because the atomic radius increases as you go down the group. And because of this, the attractive force between the proton and electron decreases, and therefore the melting point will decrease as you move down the group. So let's go on to group 2. I'm not sure if they are called alkali metals. I'll have to check, but people are saying it's not, so I'll check again. Now, these are from my notes, and group 2 physical properties. You only need to know the physical properties of group 2. And because they are in group 2, they have 2 electrons in their outermost shell. So all of group 2 elements will form +2 charge. They form +2 charge, and since they are positive, right? They are positive because they lose 2 electrons. They are called cations. Remember, cations are positive ions, and someone said it is kind of same name, just second one has alkali earth metals. All right, I'll check that again. But the positive ions are called cations, and cations are smaller than atoms. What do I mean by this? Because cations, right? Cations, they lose electrons. So let's say this is the outermost shell and it has 2 electrons. And let's say that this is magnesium, right? Magnesium has 2 electrons in the outermost shell. They lose these 2 electrons, so they'll lose this shell and they'll become smaller. So cations are smaller than the normal atoms because they lose electrons. Now, again, atomic radius for group 2 down the group increases, and ionization energy decreases down the group. Why is that? Again, because there is an increase in number of electrons, so the shell number increases, and shielding effect also increases, therefore atomic radius increases. And attraction for the outermost electron decreases, so this connects to ionization energy, and therefore ionization energy would decrease as well. So this was really what you need to know about group 2 elements. Now, in the A-level syllabus, there is reactions that you need to know, but for the IMAT, it doesn't say anything about reactions, so I'll not do that. Moving on to transition elements. For the IMAT syllabus, you only need to know the trends. You don't need to know the reactions that happen. So transition elements are very hard and strong metals that are good conductors of heat and electricity. So the reason that we use copper is because it's a good conductor and it's a transition element. So they have very high melting points and are highly dense metals. They have high density and high melting point. This is another reason we use copper, because copper has high melting point. For example, the melting point of titanium is around 7,000 degrees, whereas potassium, which is a group 1 metal, only has 63 degrees as the melting point. So potassium group 1 has low melting point. It is around 63 degrees, but titanium, which is a transition element, will have almost around 7,000 degree Celsius as the melting point, and that's huge. So transition elements have high melting points and high density. Transition elements form colored compounds and often have more than one oxidation state. What do I mean by oxidation state? For example, magnesium is in group 2, right? So it will lose 2 electrons and form magnesium 2 plus. But this is not the case for transition elements. They can form a number of different cations. So suppose copper can form +2. Copper can also form +4 or +1. The oxidation state really is different in transition elements. For example, iron can form Fe2 plus and Fe3 plus. So iron can lose 2 electrons as well as 3 electrons. But magnesium can't. Magnesium can only lose 2 electrons. Now, these colored compounds are responsible for the pigments in paints and colors of gemstone and rocks. So transition elements, right, are colored, and these pigments are used in paints And the color of gemstone and rocks are also because of transition elements. Now, transition elements, right, as elements or in compounds often act as catalyst to improve the rate of reaction in industrial processes. This, for example, when you make ammonia, right? When you make ammonia, you use a transition element as the catalyst. When you react hydrogen with nitrogen, you make ammonia. This is an industrial process, and this requires a transition element as the catalyst. So transition element catalyst of platinum and rhodium are also used in car exhaust in catalytic converters to reduce the level of nitrogen oxide and carbon monoxide produced. Ignore this part, but just remember that in car exhaust, you have catalytic converters, right? And these converters use platinum and rhodium as the catalyst to reduce the level of pollution. This was really transition elements. And now I move to noble gases. The noble gases are, remember, they are group zero, the last group of the periodic table, and they are non-metals and have very low melting and boiling point, and they are monoatomic. In the last class, I told you what diatomic and monoatomic means. Diatomic is when an element exists as two atoms bonded together in its natural state. For example, oxygen, you will find oxygen as O2 in its natural state. But group 2 elements, right, like helium, you'll find it as helium itself, one atom. So helium are monoatomic, they are single atoms, and they are colorless. Remember, noble gases are colorless. So in the IMAT, they can ask you to figure out what an element is using these trends. So they can say that, hey, the element is colorless, it's monatomic, it has low melting point. What's the element? So they will give you examples like helium, magnesium, and transition element like copper, and they'll give you 3, 4 options. You have to say which one is the right element. So moving on, right? Group zero elements or the noble gases have full outer shells. What do I mean by this? The last shell, right? The outermost shell of a noble gas is completely filled with 8 electrons. They can't remove or gain any electron because they already have 8 electrons in their outermost shell. So they don't really form ions. So group zero elements don't form doesn't form ions because they have a complete outer shell. This electronic configuration is extremely stable, so these elements are unreactive and inert. So for an element to be reactive, it has to gain or remove electrons to form bonds, right? But since noble gases have complete outer shell, they can't really react because they don't need or they don't need to remove or gain electrons, so they are unreactive and inert. Inert basically means they don't really react. I think this was noble gases, right? So yeah, moving on to halogens. Halogens are, I told you, group 17 or group 7: chlorine, bromine, iodine. All of halogens are diatomic, meaning in the natural state there will be 2 atoms, F2, Cl2, Br2, I2, and they are simple molecular. For now, you don't need to know what's simple molecular. We'll do this in chapter 5. You do need to know the colors of halogens though. Fluorine in its natural state is pale yellow. Chlorine is greenish, bromine is brown, iodine is dark gray solid. And in its natural state, fluorine is a gas, chlorine is a gas, bromine is a liquid, iodine is a solid. This you don't need to know solutions because they won't really give you solution questions. So the atomic radius again increases from fluorine to iodine. So down the group, right? When you go down the group, the atomic radius would increase. And the ionic radius decreases from fluorine to iodine. What is the ionic radius? When fluorine exists as an ion, right? F negative one, and iodine exists as an ion, iodide, right? The atomic radius would decrease when they are in ions. And remember, halogens, when they are ions, right? You add and De at the end. So bromine in natural state, when it's an ion, you call it bromide. You add IDE at the end. Iodine, you call it iodide. Fluorine, you call it fluoride, like this. And so I told you earlier, reactivity of halogens decreases down the group. So again, when you go down the group, the reactivity would decrease. This is due to the fact that the atomic radius increases in size with an increase of electronic energy levels. So the electronic shells increases, atomic radius increases. This lessens the attraction for valence electrons. I told you this earlier. So this decreases the electronegativity. I'll explain what electronegativity is. But for now, two things you need to know for halogens. The reactivity would decrease down the group, and the atomic radius would increase down the group. So the last thing you need to know for trends is period number 3. What is period 3? Let me go to the periodic table. So period 3 is this right here, going from sodium to argon. This is period number 1. Hydrogen, where hydrogen and helium are present. This is period 1. Period 2 is where boron is present, and period 3 is going from sodium to argon, right? So what you really need to know is the melting point of these elements. So sodium to argon, sodium is +1 and argon is inert, so it doesn't really have a oxidation state. And ignore this will come in chapter 5. But the melting point from sodium is low. For going from magnesium to silicon, it's high, and from P to Ar, which is argon, it's low. So again, Na has low melting point because it's group 1 alkali metal, and then magnesium and aluminum have similar melting points. It's usually higher than sodium. Silicon is the element which has the highest melting point. The reason for this is because it's a macromolecular element. I'll explain what this is again in chapter 5. Silicon, because of it being macromolecular, it has the highest melting point. It's around 1400 degrees, whereas magnesium and aluminum both have around 800 degree as the melting point. Sodium, I said it's around 63 degrees. Na is sodium, it's around 63 degrees. And from silicon onwards, the melting point would decrease. So let me go back to the periodic table, right? So from phosphorus to argon, the melting point would decrease because these are simple molecular. You don't need to know what simple molecular is. They are only simple molecular, and argon has the lowest melting point because it is unreactive and it has a complete out shell. Because of this, it will have a low melting point. So this was really everything, all of the trends. You need to know period 3 trends, the halogen trends, and then the noble gases, the transition elements, group 1 and group 2 trends, the atomic radius, the ionization energy and electron affinity. And you can memorize this diagram right here. It's very important that you memorize this. You can take a screenshot if you want, or I'll send this in the Discord server. So let's solve this question. You guys have 1 minute to solve this question. I think this is from IMAT 2011, the last question. I think it's question 59. I don't remember exactly, but it's from 2011. So you have 2 minutes to solve this. C. Someone said C. Okay, so let's do this question. So which of the following shows how the atomic radius of element changes across from going from left to right? So left to right in the row of the periodic table from potassium to bromine. So where is potassium? This is potassium and this is bromine. So they're saying this is related to group period 3. Remember, this is period 1, period 2. This is period 3. Sorry, this is period 4. D. Someone said D. So what did I tell you earlier? I said that you have to memorize where is that diagram. Yeah, right here. So atomic radius across going from left to right decreases, right? So when I go back to that question, I know that my atomic radius is decreasing across going from left to right. My atomic radius decreases. So potassium to calcium, my atomic radius is decreasing. So decreasing, decreasing, decreasing. It's either A, B, or C. I can cancel out D or E. Would they ask us questions like this on the IMAT since we won't have a periodic table? Yes, they'll ask you. This is a question from the IMAT. Because you don't have the periodic table, you have to memorize the trends. Everything I taught you, you have to memorize that. So it's either A, B, or C. Going from Sc to zinc, where is Sc to zinc? The periodic, the trend is it's decreasing. So it's decreasing, decreasing, and gallium to bromine, the atomic radius is decreasing. So decreasing. So the answer is C. So for the people who said C, congratulations.